How are we doing today? Doing all right? Wonderful. Okay, so today we're going to finish the first handful of sections of Chapter 2 through 2.3. Okay. 2.1 was about integrating factors, and 2.2 has to do with separable equations. Okay. And then 2.3 is going to introduce a handful of examples that are applications um, related to physics or chemistry or something that we can solve using the techniques that we have learned up to this point, namely separable equations and linear first order equations solved by integrating factors. Okay, so let's get going here. So there was one thing that I forgot to open up. All right. Here we go. Okay, so let's start getting warmed up by just doing some practice for computing the solution to some separable equations. All right, so what I'm going to do is I'm just going to select some problems that show up here in the exercise list for section 2.2. What looks like a good one? So we have y prime equals 3x squared minus 1 divided by the quantity 3 plus 2y. Okay. And what we want to do is take advantage of the fact that the variables here are separated and integrate both sides, and then if we can, isolate the variable y. Okay, so let's take a look at this. We can rewrite this after multiplying through with the denominator on both sides of the equation. And with the denominator here, or sorry, with the denominator removed, we can now integrate both sides of the equation with respect to technically x, but we just kind of follow the symbology and do y and x. So we have 3y plus y squared on the left-hand side. And then on the right-hand side, we have x cubed minus x plus c. Okay, just the power rule. All right. Now, with this expression, we would like to isolate y. Okay. At first blush, it looks like maybe we can't do that, but we're better than that. Okay. What we can do is notice that this is the first two terms of a quadratic polynomial. Okay. So what we can do is complete the square. So what we're going to do is the pattern that we're trying to match is this. A plus b quantity squared equals a squared plus 2ab plus b squared. Okay? We have to add the piece that's missing, right? So when I look at 3 times y, I have to think about 3 times y as 2 times something, right? Based on this, one of those somethings is very clearly y, because I need y squared, right? for A. So what I need to do is rewrite it to look like this. 2 times something times y. Okay? That means that B is 3/2. So to complete the square, we add 3/2 squared, and I'm not allowed to just add a number to the equation, so I have to subtract the same value. So I'm adding 0. And then what we can do is combine this part into a square. So this becomes y plus 3/2 quantity squared. And then this, because it's just a constant, I can put it over with the constant integration. Right? Some fixed but arbitrary number plus 9/4 is still some fixed but arbitrary number. Okay? And so from here, we can come up with a formula for y. There's a plus or minus in the equation because we had to take the square root of both sides to get y out from underneath the square quantity. And whether it's plus or minus will be something that would be determined by any initial conditions that we apply to the problem. Okay, so if I give you an initial value in addition to this problem, then that would force it to either be the plus or minus branch of the square root. All right, questions about this? Seems okay? All right. Let's take a look at another one. Look at one where the book gives us an initial value to work with, and then do a plot. What looks interesting? We'll do that. All right, so we have y prime is equal to e to the minus x minus e to the x divided by the quantity 2y minus 5. And our initial value for this problem is going to be y of 0 is 1. So at x equals 0, y equals 1. Okay. We don't have to do any extra work to separate variables. We can just multiply both sides by the denominator. That gives us an expression similar to what we had last time. We can, again, integrate both sides of the equation. This gives us our value here. Right? This is easy to integrate. It's just a simple U substitution. I pick up a minus sign. Okay. Okay. We see that we're kind of in a similar situation where we were before. We can get y by itself, right? If we complete the square again. I'll skip the Technicolor presentation this time. But we need half of 5, and then we square it, which is where we get 25 fourths. Okay? We add and subtract it to add 0. And we can do the same thing where the negative 25 force gets absorbed by the constant of integration. Okay? This all makes sense so far? Okay, I made a copy mistake. Thank you. Sorry. I had a negative on that exponent that should not have been there. Thank you. Yeah, all right. Someone in the chat had it too. Thank you. Someone in the chat is asking if we can skip the plus or minus, or adding 25 force and subtracting 25 force. You don't want to skip that part because the whole point is to complete the square. So you have to figure out what that constant is to make sure that you're adding the right thing. Okay? Yeah. The only thing that's happening is we use that step, but the extra added term we don't have to pay very close attention to because when we solve the initial value problem, that whole thing's going to sort itself out. I can show you a situation where it is important to track the negative 25 force, but I want to do the regular version of the problem first, and then we'll go back and reevaluate. Okay? So we're at the set of steps that we were to finish the other problem. We can take the square root of both sides. Since we're taking the square root, we have the plus or minus in front of the radical. And then we add 5/2 to both sides. And then we can write this in a slightly more condensed form if we want, by taking advantage of the fact that addition is associative and commutative. And so this is our solution to the general differential equation. Okay. The next step is to apply our initial condition. And so we say that 1 is equal to 5/2 plus or minus the square root of c minus e to the 0 minus e to the 0. Yeah, we're going to find out that that has to be the case. You're correct. All right, so we have this expression here. And then e to the 0, of course, is 1. So this is I'm out of room on the page, so let's grab another page. We can move the 5 halves over to the other side. We have our plus or minus here. This is c minus 2. So this is negative 3 halves. We know that we're going to have to take the negative root. We have c minus 2. We're going to just square both sides now to get rid of the square root. And so we get that c is 17/4. All right, that makes sense? Doing okay? All right. So the solution to our initial value problem should have the form 5 halves minus the square root of 17/4 minus e to the negative x minus e to the x. Okay. Let's take a look at this. We have our function is equal to 5 halves minus the square root of 17/4 minus the exponential of negative x minus the exponential of x. Okay, we could have typed e to the x too, right? We see that our initial condition is satisfied, right? Okay, and this is what it says that the form of this plot is. Okay. Now, if we looked at the direction field, I did not type the right thing, but it might give me the right thing anyway. Okay, so we have this example here, and then we can put in our ODE. It was I have to put these in parentheses. Two y minus 5. Okay. All right. So there's our expression. And what we want to do here is change these things around so we can see a little bit more about what's going on with the direction field. And then we can zoom in here. We see that there's some swirling or something going on, right? And if we grab this other expression here, we can plot it to see that it fits in with what's going on with our function. Okay. If we had been given some different information about what's going on with this, we would get different types of curves. Okay. And one of the things that we could have worked out was, what does this look like with any possible initial condition? Okay. Sorry, what? I will be more specific about that when I write it up. There's another question. Okay. Someone in the chat asked why we don't have the plus or minus in the final solution. The reason that we don't have both is because the initial condition says that the solution has to pass through the point 0, 1. Okay. If I have that condition, it's only possible for me to be on one branch of the plus or minus. It forces me to be on one side of them. There's no way that I can have 5 halves plus something that I'm legally allowed to have underneath the square root that's going to give me 1. Okay, so it's impossible. It doesn't satisfy the initial condition, so that's why that part of the solution goes away. All right, now, one of the things that could have been done differently about this is if instead of setting 0, 1 as the initial condition, we could pick some other value. Okay, we could have set it up to where we don't specify necessarily what those points are. X is equal to A, Y is equal to B, and then just figure out what the general form of the solution would look like in that case. So let me make a copy of this. Okay. We are using this as our condition. And so B is equal to 5 halves plus or minus the square root of C minus e to the negative A minus e to the A. And what we want to do is try to figure out an expression for C. Okay. Now, I don't want to write this a bunch of times. Okay. So will you allow me to write this? They're the same. Okay. Definition of the hyperbolic cosine. 1/2 or e to the x minus or plus e to the minus x all over 2. Okay. I'm trying to remind you all of things. These little identities and stuff pop up kind of all over the place. Anywho, sorry, that should be -2 here. Okay, so we have b equals 5/2 plus or minus the square root of c minus 2 hyperbolic cosine of a. And then we want to get c by itself. So we have b minus 5/2 equals plus or minus the square root of c minus this. Square both sides. We get this. And so this is our expression for c. b minus 5/2 squared plus 2 times the hyperbolic cosine of a. All right. Now, in general, we don't do this sort of computation very often. Okay. The reason that I wanted to do it was so that I could demonstrate for you the thing that I'm about to put on screen. Okay. To show you how the solution would change as the initial condition is being modified. Okay. All right. So we have, I'm going to make a new function, call it g of x. I will turn this off for now. If you click the thing in the leftmost bit here, you can turn off graphs or something if you don't want something to display. Okay, so this is going to be 5/2, and then we'll show the plus and minus branches just to see how that affects things. So I'll make a second function here in a second. Okay, so this is going to be c minus 2 hyperbolic cosine of a, or sorry, of x. And for c, instead of having it be a slider, we want it to be b minus 5/2 squared, not that squared, this squared. Sorry, I'm a tiny bit out of practice for knowing when the stuff is going to show up here. Okay, and then what I should have done was make there. Okay, so this is my point AB. We're going to be moving this point around, and then we can see that the solution changes based on where this point is, and the solution has to pass through it, right? Okay. We can, likewise to what we have here, make the other branch for the solution with the minus sign. Okay, and we see that we get this closed loop shape. Okay, so it was okay, maybe, to have the plus branch on here, but the minus branch was the one that gave us what the value of the initial condition was. So we have to do some extra work before we know for sure if we just have would have the top branch or if we have both halves of the function. Sometimes we only have one of them. Okay, in this case, it makes sense to look at both. All right, but now, if we drag this point around, okay, we see that we kind of have this like rounded rectangle shape that gets closer and closer to being an ellipsoid the closer that my point gets to this sort of vortex point here, right? This is where all the action is. Okay. And so that's what the solution looks like, and how you would, if you wanted to know complete information about all solutions to the initial value problem, you can plot your direction field. And then after you've plotted your direction field, if you are capable of solving the associated differential equation, which we can, because in this case it was separable, you can work in a general initial condition to your formula, and then use some program like this in order to change the initial condition on the fly so that you can see all the different integral curve shapes that give you a solution to the differential equation. Okay? All right, questions about this? Seems okay? All right. So, it's a bit expanded discussion of section 2.2. Okay, let's look at section 2.3 now. Okay, there's some useful stuff to read through here. For this section, the write-up is a bit of a condensing and in certain places adding more detail to the discussion that goes on in the textbook. But it is important when we are working with mathematical models that are meant to represent physical problems to take care as we are putting our model together. Okay, there are always going to be elements to this, and the whole point is that it's a model and it is not supposed to be a perfect representation of what happens. It is supposed to give us the ability to, within a reasonable amount of accuracy and under reasonable conditions, make an estimation about how the behavior of that system is going to be. Okay. Now, this is our first course in differential equations, and the assumptions that we make about our models are going to be fairly significant, okay? Because we are still limited in our ability to solve sophisticated differential equations. And with less restrictive assumptions comes more difficult to solve equations, so we're erring on the side of caution for the time being. Okay? All right. So the basic steps are that we construct the model, okay? The model is going to be based on some relatively simple premises, okay? There's going to be forces that we're interested in analyzing, or there's going to be some particular growth rate that we're interested in analyzing, say bacterial growth or radioactive decay, something like that, okay? And then we put that information together. We come up with a model, and then we look at it, see whether or not it on the surface makes sense, and then employ that model to come up with the solution to the differential equation. We look at the resulting solution and then compare that solution to data that we can measure, or our gross knowledge of the physics involved and how things behave based on how we see them, and then we can make a determination about whether our model does a good job of dealing with the case that we were trying to work with, or if the behavior is more complicated than the model that we have come up with allows for, or if the range of situations that we are trying to use our model within do not apply to the solution. Okay? So there are several different things that can be limited, that our model can be limited by. All right? If we're talking about an airplane flying through the sky, okay, there isn't one model that we would use that could deal with all different types of aircraft. Okay? Because different types of aircraft fly under different kinds of conditions, right? What it means to be stable flight for someone's personal aircraft that they use basically as a hobbyist is going to be different than the stable flight that you would see for an airliner is going to be different from the kind of stable flight that you would see for an air refueling type plane, or a fighter jet, or something insane like an SR-71, right? All those things behave completely differently flying under their normal conditions. So we need to have different models to handle each of those things. Okay? All right. So let's start with one of the kind of most common and prevalent examples of modeling using differential equations. And this is the mixing tank. We start off with a tank, and the tank has a solution in it, okay? A mixture of usually water, but some sort of solvent, and a solute that is dissolved in that solvent, hence a solution, right? Okay. The example that you'll see most common in your textbooks are salt water or some kind of polluted pond or something like that, okay? But technically this works for any solution. The idea is that we have some amount of stuff dissolved in our solvent, and we are mixing in the tank at a very high rate, okay? So the main assumption that we make, or there are two main assumptions that we make for this problem. Number one is that if I add new solution to my container, that it's mixed fast enough that I can't tell, okay? So say you're doing something like making Kool-Aid, I don't know, all right? You have two different pitchers of Kool-Aid, all right? You have some regular Kool-Aid and then some terrible Kool-Aid that your aunt made that she didn't put enough sugar in or something, okay? And you're trying to mix them to somehow save the whole thing, all right? If you pour the bad Kool-Aid into the good Kool-Aid, why would you do that? I don't know. But if you're pouring them, all right, they have to be stirred up before the sugar content of the entire pitcher would be even, right? Okay, we are assuming that that process happens instantaneously. Okay, so if I add stuff with a different concentration, we are assuming that the mixer is fast enough that we can't measure, and the mixing happens right away. Okay, the other thing that we're going to be assuming is that, just for the sake of simplicity, that the amount of volume of solvent in the tank remains constant. So I'm pouring stuff into the tank and I'm draining stuff out of the tank, and I'm doing so that the amount of fluid in the tank remains the same. This makes the differential equation easier. Okay? So those are the two assumptions. All right? And so what we're going to be looking at is we have our tank. We have the pipe into the tank, the pipe out of the tank, and the bottom of the tank, and some stuff in here. Okay? And that's pouring in there. All right? The differential equation that you saw on the other screen said dq dt equals rate in minus rate out. Okay? The variables for this setup are obviously t is time. Okay? We're going to have r, which is a flow rate. It's going to be constant, but it matters what that is. Okay? We may have a volume of the fluid in the tank. That'd be something that's given to us as part of the just initial information to set up for the problem. Okay? And most importantly, this is the thing that people find the hardest to remember. is that Q, the thing that is the function that we are solving for, is the amount of mass of solute. Okay? If we're talking about salt water, it's how much does the salt weigh? Or what's the mass of the salt? It is the amount of stuff that's dissolved in the water. Okay? So this differential equation describes the rate at which the mass of the solute is changing with respect to time. Okay? Because if we're adding stuff into the tank and then draining stuff out of the bottom of the tank, okay, there's going to be a change in mass of dissolved stuff. Okay? And that's what this differential equation is looking at. It's looking at the change in the mass of the dissolved stuff. Okay? So let's set up an example here. At time 0, a tank has some amount Okay, so we have Q sub 0 pounds of salt dissolved in 100 gallons of water. What we want to do is suppose we'll call it salt water. Salt water containing 1/5 a pound of salt per gallon is entering the tank at a rate of R gallons per minute. Okay. The solution is draining at the same rate. Okay. And what we want to do is to determine an equation that will tell us the mass of salt in the tank at time t. Okay. Does this make sense so far? Okay, we're told what the initial concentration of the salt water in the tank is. Okay. All right. We can either be told the concentration and the volume of the tank, or just how much mass of salt there is, right? But we need to know the volume of the tank in order to be able to do the problem correctly. Okay? Our differential equation is given to us as dq dt and in order to construct this model correctly, we need to make sure that our units for whatever we're doing are set up correctly. Okay? Now, we're told that rate in minus rate out was the setup for this. Okay? So let's start with the rate in. Suppose that salt water containing 1/5 pound of salt per gallon is entering the tank at a rate of R gallons per minute. Okay? So that is 1/5 pounds times R gallons per minute. Okay, sorry, the time measure is in minutes, excuse me. Okay. And then the 1/5 is a concentration, so it's pounds per gallon. Sorry, I forgot to write that part down. Okay, now looking at this, we want the units to match, right? Don't the gallons divide out? We're left with pounds per minute. Okay, so the first term in our differential equation is going to be R over 5. For the second term in our differential equation, we need to determine the rate out. This is where our assumption of the solution being well mixed comes in. Okay, we know that any salt added to the tank is immediately incorporated with the salt that's already in the tank. Okay, so that makes the second term easier to write. And we need to know the rate of salt as it flows out of the tank. But in order to be able to determine that, we need to know how much salt is in the tank. Right? Now, at any given time, how much salt is in the tank? Sorry, what? Huh? That's the volume of water, right? 1/5 is the concentration of the salt that's entering the tank. That's what's being poured in. What we're trying to figure out is what's the concentration of what's being drained out. And what's being drained out is the well mixed solution, right? Okay. So it is the completely dissolved salt in the whole tank, right? So the concentration of that is the mass of salt in the whole tank divided by the volume, right? We know the volume, it's 100 gallons. How much salt is in the tank? Huh? Q naught is how much salt we start with. And so the amount at the current time is just, you're really close. It's just Q, because it's a differential equation, right? We have to solve for something. That's the function we're solving for. Okay? So we have Q pounds of salt, right? We have 100 gallons that salt is dissolved in, and the rate that it's flowing out is R gallons per minute. Make sense? All right. Somebody's struggling back there. Okay. Anyway, so same deal. The gallons divide out, and we have pounds per minute, which is the units that we should have, right? So both of these are a concentration and a flow rate. Make sense? Okay. So I wanted to go through the unit analysis on this because it's important to know how to set these things up. All right. Especially if you're doing a problem you've never seen before, the easiest thing to do is just make sure the units work, right? You're not guessing in the dark. You're modeling a physical system. Okay. It has to be consistent, and at very minimum, the units have to match. So use those as a guide. Okay. So we can simplify what this looks like. To put it into this form, okay? Or if we want to do a little bit of factoring, we can write it like this. Okay? From here, this is both a separable equation and a first-order linear equation. Okay? R is just a number, okay? It's not specified, but it's a number. Okay, Q is the variable and T is the independent variable. So any of the techniques that you know from our previous couple of sections will work here. And working through the problem here. Okay. There's a video example where I go through that you can check out later, working through all the details to come up with the solution. Okay. I'm going to skip this for now because I want to talk about another example before we run out of time. But separable equation, and then the steps to finish it up are handled right here. Okay. Next up, another type of example has to do with finance, okay, which is something that we all need to understand the rudiments of, even if it's not the most fun thing to pay attention to. But here we have a problem that is set up with an interesting condition that kind of goes beyond the basic analysis that maybe you're used to. Okay. We have at the top of this block here a basic exponential growth problem, right? ds dt equals r times s, where r is some fixed rate and s is the amount of stuff. Okay, in this instance, we're talking about a sum of money. All right. Now, one of the adjustments that can be made to this problem is by adding to the differential equation some value k here. Okay. And the k represents regular payments. Okay. So most of the financial instruments that we interact with are things where there's some very large sum that you start with, and then, or maybe some small sum that you start with, and then you either pay in if you're trying to do something like have a savings account, or if it's a bill, it's something you're trying to pay down, right? And so that's the role that K fills in this instance, would be that regular payment value. And so what you do is, again, this, just like the equation that we wrote down, ends up being a first order linear equation that is also separable. Okay, so you can solve it as a separable equation or as a first order linear equation with integrating factors. Okay, in the example typed up here, it's solved by an integrating factor. And you can cough up the solution of the differential equation and apply a generic initial condition s at 0 equals s naught to figure out that the sum of money would be the exponential growth equation, s naught e to the rt, plus the adjustment for those regular payments that are being made. Okay. K is a positive number if you're adding money, so it's a savings account. K is a negative number if it's a bill that you're trying to pay down. Okay. And what you're fighting against or working with, depending on the situation, is the exponential growth part of the problem, right? So, for instance, if you have some nonsense like student loans, okay, you have to make payments that are big enough to actually be able to beat the interest that's being accrued by the rest of the account, right? And if the payments that you're making aren't big enough to beat the interest rate, then you're underwater forever, okay? This is also the same kind of thing that can happen with people and mortgages, okay? You can have a mortgage that you owe a bunch of money on, and if the payments that you're making and the value of the home don't keep pace with inflation and the amount of money that you owe on the mortgage, you can be in a bad way as well. Okay, but this is the basic mathematical structure of how those things work. Half of you look terrified now. Anyway, all right. Oh, I know. Yeah, no, the housing market is. I am not much older than most of the people, or at least in this room, and probably enrolled in the class overall that are watching on the internet. I am tired of living through generational economic crises. We're on the fourth since I've been alive. It's pretty bad. There was the terrible stuff that happened as a result of 9/11, and then the housing market collapsed in the late part of in 2008. And we've had the pandemic, and the housing market's about to collapse again. I'm over it. Anyway, okay. So here is an application of the problem that we just talked about. Okay. The write-up here is using. I must have done that in MATLAB. Okay. So MATLAB is used to do these computations, and the idea is that we want to show some different curves for total money that you would have after saving for a number of decades, based on different starting values and how much money you're allowed or you can afford to put away every year. Okay, so more or less a demonstration of the power of exponential growth. Okay, And you'll notice that the total amount that you're able to invest, if you can increase that by a few $100s per year and manage to keep it up for a handful of decades, that it gets pretty significant. Okay. Now, having boosts to the interest rate is helpful. Okay. 8% may be a little bit pie in the sky for the current economic environment, but that's how it goes. Okay. And the lesson to be learned here is that time is the most important factor in these computations. Okay. It helps if you can save more money, okay, per year. But the main thing is how long can you wait before you have to start drawing on this? Or how long can you allow it to go? All right. Because if essentially what happens is that there's a time scale on which the amount of money doubles, right? So if we look at what's going on here, we look at the time it takes us to get from zero to $200,000. Okay, it's about 27 years, right? The time it takes that money to double once you have it is 7 or 8 years. Okay, and then you look at how long it takes for that to double again. All right, and you see that the time compression happens and is pretty impressive, right? Okay, so we go, it takes us almost 30 years to get to $200,000. And then it takes us another 7 or so, 7 or 8 to double that. And then double that $40,000 less than 10 years. Okay? So the big swing on this curve happens at about the 4th decade, right? So I know that all of you are in your 20s or maybe 30s or something like that, but if you plan on being around in your 60s and 70s, like, start now, okay? Because you want to have access to the extra funds before you're completely broken down and can't do a whole lot of stuff, right? We all hope, of course, our healthcare system will sort itself out and let people stick around a little bit longer. But yeah, well, life expectancy has slowly been increasing, but it's one of those things where if we did it right, it could be a lot better than it is, you know. And who knows? You might have to do this to be able to afford healthcare if it doesn't go the right way. Anywho, yeah. Someone in the chat mentioned that their folks' advice was to not buy a house, which, depending on your perspective, could be a trap. In the current housing market, of course, buying a house is probably a bad idea because the prices are really inflated. But generationally, one of the easiest ways to develop long-standing wealth is to own property. And the reason why a lot of people who have extra money are buying property is because it's stuff that has inherent value that folks eventually are going to want, right? So they're buying all this stuff and basically sitting on it because they have the extra money and can afford to lose money in the time being while the prices are inflated in the hopes that someone will buy it. And it's they're going to have to sit on it and lose a lot of money, including things like the interest rates going back to normal instead of being a pittance is what they are right now, for that to happen. And then yes, if the person in the chat mentioned that the people who gave them their advice have owned a house for about 30 years, and that's it can start to get expensive, you know. Houses around the 20 to 50 year range start needing things fixed, and then if it's the wrong kind of stuff that needs fixed, then that's bad. foundation problems, of course, are horrendously expensive, or if you happen to have built a house that doesn't have central air and decide that you need that, also not the best, or want to do something like finish an unfinished basement. Anyway, so I need still to post your quiz for this week. I'll make sure that that's available in the morning so that everyone can take a look at it. I have a class at 11:30 tomorrow. I'll try to make sure that that's posted before I take off or before I head up here to teach that other class. You have that to work on over the weekend. And then I will also post a key for the first quiz and then get the grades posted for those sometime probably early next week. I'm not sure that I have a typed quiz key for quiz 1, so I may just write up a thing like the notes and make a PDF file or something for everyone to take a peek at. But pretty sure I've already typed up the quiz 2 key, so I'll have that to post when that comes due. All right? May I have any questions? Sorry, what? I'm gonna do that. I'm gonna do that tomorrow morning. I'll probably make it due Monday or something. I'll have plenty of time. All right. Everybody here is quiet. Anyway, I guess we'll call it there. If you do have questions that come up, or if by some chance I forget to post the quiz tomorrow morning, send me an email and I'll make sure that's taken care of. And then I will see everybody after the weekend. Take care. Have a good one.